Hello again, everyone. Today we're going to start our first content module of the course. This is really an opportunity for you to sort of get a little bit of information about sampling, which is something that you can learn about also in the Forestier textbook, but of course I want to provide you with some substitute for a regular class meeting, and in doing so, give you at least a chance to, at least see this content in a more audiovisual format than you would otherwise. I think that it's also helpful just to have a little bit of a semblance of normalcy here, to see something that you would probably otherwise see if you were to be in the classroom today. So why don't we get started with this discussion of sampling. This is really an important concept from the perspective of large N research. So if you recall, long ago before spring break, that time that we had class in person, the very last thing that we talked about was this debate, this sort of ongoing controversy between large N or quantitative scholars in the discipline and qualitative scholars in the discipline who are mostly interested in studying thick description, or sort of taking a small number of cases and learning robustly a lot of information about those individual cases to build sort of the theoretical linkages between different phenomena. Large N researchers are, of course, more interested in trying to adhere to some of the principles that come to us from statistical reasoning about the generalizability and the validity of their estimates. And so sampling is one of the ways in which we can be relatively certain that we're getting closer and closer to estimating real sort of statistics in a population. And so one of the ways that we know that sampling is effective at getting us closer and closer to understanding what's really happening in the research population we care about is this thing, the weak law of large numbers. And so the weak law of large numbers is essentially this. As a sample gets bigger, right, as large N becomes larger, basically, our samples are going to get better and better at approximating the population parameter that we care about. And we'll see for a working example of this in just a second. Population parameters, of course, the definition of that is the characteristics of the population that we actually want to measure. So again, this is a quantitative large N kind of assumption, but because we are doing some quantitative research in this course, it's important to learn about. So here's the example I want to give you. This is kind of a silly example, and it turns out to be, it's kind of a stupid pun, so bear with me if you will, but let's imagine this 10-mile run. It's this run that the race organizers have set up, and they've done this in a very peculiar way, and actually a way that probably only statisticians or people who are in need of social quarantining or social distancing would ever set up. And that is, this run is sequential in terms of each runner doing the course. So the first runner, the gun goes off and only one runner takes the course. And they finish the entire race, and then the gun goes off again, and runner number 2 then gets to run the entire course and finish. So again, you can see it's a great way to practice social distancing, but a pretty weird way to run a race, because of course if you had thousands of runners, it would take you forever to actually get this race finished. People would be running throughout the night. But so it's kind of this, it's almost like passing a baton here. We've got a 10-miler, but every participant runs the race individually and in sequential order. And so what we're interested in, the research question we're interested in as these race organizers is, how fast does the average runner run a 10-mile run? We want to know about this quantity of interest. Of course, we could think about all kinds of different research questions that relate to this. So maybe we were interested in looking at the relationship between finishing time and, I don't know, say like nutrition or something. Maybe runners who are on a purely vegetarian diet do better or worse. I don't know what the research question is. But we want to know, our first sort of research question is descriptive. We want to know what is the average finishing time of a participant. And so if we were to do this, the gun goes off and the very first runner, as we said, runs the race and then finishes. And we record their time, and it turns out it's a very decent 87.8 minutes. And so based on that information, if we were to have a data set consisting of one observation, and we were trying to understand what the average finishing time was, what information do we have to go off of? Just that one person's time. And so we would say, aha, we have calculated the mean finishing time. It's 87.8 over the number of runners who participated, which is 1. And so therefore, we can assume that the mean finishing time for the average person is 87.8 minutes. Now, of course, that's probably a pretty bad estimate because we've only collected data from one person. If we got a second person in there and they finished much slower, we would see that difference, right? This person finished, 20 plus minutes slower than the previous person, we can see that calculating the mean among those two people actually substantially changes our mean estimate by over 12 minutes. And so then if we let the third runner run, the fourth runner run, and we keep measuring these things and keep calculating the mean across more and more and more respondents or runners, we're able to get better, essentially, which is what the weak law of large numbers tells us, at calculating the true mean of the population of runners. So this is why this is a pun, is that this is known as the running mean. And so if we imagined that I set this up as a simulation and I actually knew the real mean time of all runners in our population, which in fact I did, we're able to actually visualize how the running mean gets closer and closer to that true mean as we go. So here's kind of that image. I created this in R. You'll see that basically what I did was I set up this true mean. I said, here's the actual mean in the population of runners, which is unknown usually in our research projects because there's no way to know the true mean of a population unless we did some kind of census, right? If I were to sample these sequentially, I basically said, hey, give me a random participant, 1, 2, 3, 4, 5, 6, all the way up to 100. As we go, as it turns out, even though there are some minor deviations across time based on some of these runners in the middle cluster were really fast, some of these runners were a little slower, as we go, we actually get closer and closer and closer to that true mean. And so that's a really powerful finding. What that tells us is that a sample of 4 people is a pretty bad sample in terms of trying to understand population parameters. But a sample of 100, that could actually get us pretty close to the actual running mean of these runners. So that's really, really helpful, a very useful quantity in our statistical toolbox. But this isn't the only way that we can use statistics to help us understand our populations. So the central limit theorem is the second of 2 concepts that I want to introduce to you today. And this is really something that helps us to understand not just whether we're getting closer to the population parameter, which is what we care about. It also helps us think about exactly how uncertain are we? Are we getting pretty close to the actual mean? Are we still fairly far away? You know, what is the size, basically, of this gap between the truth and our estimate? Because again, if we expect the gap to be pretty large or to be pretty uncertain, then that means that what we're sampling is probably not going to be super helpful to us. But if we're fairly happy with how close we're getting, then we might say, okay, we can make some inferences, we can make some research statements, we can analyze our research questions empirically, and say that we're pretty confident that we're onto something. So that's really the other thing that we care about from a statistical perspective, is how confident are we that the estimates that we've derived from samples are actually getting us close to the truth. So I've got a whole bunch of stuff on this slide. You can sort of pause the slide and read this if you'd like, but really the key thing that I want to distill from this is this idea that our estimate, right, that guess that we have as to what the actual mean is of the runner's times, that guess we can call X bar. And it turns out that X bar, on the basis of some statistical fancy footwork, basically has a lot of well-established known properties. We know that it's going to behave a certain way regardless of what it is that we're measuring. If we're measuring the width of tulip bulbs or the speed of runners or the political proclivities of Americans, it doesn't really matter. As long as we're engaging in sampling in a good way, these sample estimates that we're gathering are always going to be random variables with special properties. And so the special property that we care about is this: the idea that we can use a very simple calculation of the standard deviation of a variable and the square root of the number of observations that we've gathered to compute a standard error. It's a really, really simple equation. And what it essentially tells us is this is a standard variability estimate for essentially how close we are based on just these 2 factors to the truth at any given time. And really, the thing that we care about the most here is the idea that this thing gets better, right? This error gets smaller as the square root of n goes up, right? This is, again, something that is very consistent with the weak law of large numbers. Essentially, this is telling us that the more observations that we get as we increasingly sample, then we're going to end up having the standard error reduce, which means that we're getting closer and closer to the possibility that we're actually within a good sort of boundary for understanding the actual population parameter, which we care about. So to really sum up this kind of statement in a very sort of simple way, right? It doesn't matter what kind of weird variable we're measuring. Successive samples are always going to vary in predictable ways around a central tendency, and the central limit theorem tells us that those estimates vary according to what's essentially known as a normal distribution. And the normal distribution has these very specific properties, and at the end of the day, that means that that normal distribution is going to tighten and get us closer to the truth every time we increase our sample size. So sampling is good, it's possible, it's statistically meaningful, and it gets us closer to population estimates. So if we were to change the size of our samples, right, this is the thing that ultimately I want to get to, this is the thing I want to conclude with, is that if we were to change the size of samples, we're going to see that we are tightening essentially that margin of error, as I was saying. The sampling margin of error for any kind of survey, for example, is going to be essentially 1 over the square root of n. So that's the number of people that we've gotten to interview in our survey. So for a sample of, say, 100 people, the margin of error, just like those runners with their highly variable times, is going to be about plus or minus 10% for any, for example, a binary question. Do you approve or disapprove of the president of the United States? That margin of error is going to be quite large if we've only sampled 100 people. If we have 200 people, that margin is going to decrease a little bit. For a sample of 300, it's going to go down. And in fact, we can actually graph this again using R. As the sample size goes up, our margin of error, that is the percent in which we have the credible interval for which we believe our actual estimate lies, that actually starts to decrease in this nice kind of curvilinear pattern. So that by the time we get up to a sample size of about 1,000 people, we're getting into a margin of error rate that's below 3%. And so what that means is that because our samples are full of all sorts of random people, as long as we're doing that sampling properly and we're not oversampling by accident some group or another, we're getting closer and closer and closer to the true population estimate every time we sample a larger sample. And so this is why in large N statistical analyses, it's always better to have a larger sample size, right? Like if we were thinking about, for example, a presidential primary poll, and we asked people, who are you going to vote for in the primary, Bernie Sanders or Joe Biden, and we had a 10% margin of error, that would tell us almost nothing, right? It would say, oh, well, Biden's leading 60-40, but there's a 10% margin of error. It's almost impossible to distinguish whether or not one of those two candidates is leading in that poll. But if we had a very large sample, we were able to say that the margin of error was around 3%. We could say, oh, a 10-point lead in that poll, there is a significant and meaningful difference between those two candidates in terms of the polling. And so that, again, is why we want to have larger sample sizes. So my sort of challenge to you, my idea that I raise in this sort of video discussion, is I want you to think very carefully about how you might think about increasing the number of observations that you'd be able to gather in your statistical analysis. I've asked you to sample in a way that allows you to gather at least 50 observations in your final project. But 50 observations, as we've seen, is something that is still going to lead to a large degree of uncertainty. And so if there are ways in which you can gather more observations, I want you to strategize a little bit about that. Think about ways that you could gain a data set of 100 observations or 200 observations, right? How could you start to extend this N situation, make that data set longer, right? Again, thin description, but longer data sets in quantitative research. Think about ways that you might be able to accomplish that. And I think that you're going to find that it's going to be very helpful for you in your final projects. So I hope you enjoyed this discussion, a very brief discussion of sampling, and I look forward to seeing you in my online office hours, and stay tuned for the next module.